Brazil, the Federal University of Pernambuco, we have Dr. Leonardo Guimaraes to talk about the modeling of water and CO2 injection with potential fault reactivation. Dr. Guimaraes.
Thank you, Andrew. I'm going to share my presentation. Can you see it?
Yes, we can.
Okay. So thank you for being here for our presentation. My name is Leonardo Guimaraes, as Andrew mentioned. I am the chairman of energy simulation at Federal University of Pernambuco. It is in Recife, Pernambuco State in Brazil. The title of the chair is Multiphysics, that we understand as geomechanics and reactive transport, and also other components are optimization and uncertainty propagation. And I'm going to present you today part of our research, that is the numerical modeling of water or CO2 injection in the formable reservoirs with the possibility of fault reactivation. I would like to show a few slides on our chair program strategy. We are working in reservoir modeling and robust optimization. The main area, because the main areas that we consider are geological modeling and reservoir simulation. We have in our research program elements of these two disciplines. The proposed research can be applied for both EOR or CO2 injection for storage CCS projects. And the reservoir modeling is related. This name is because we have elements of outcrop characterization, upscaling, geomechanics, carbonating CO2 geochemistry, laboratory testing. We have a rock mechanics lab dedicated to carbonate rocks. And also based on these results from these labs, we try to build constitutive modeling for numerical analysis. Also in the robust optimization area, we have the main focus on WAG optimization, as our main fields are pre-salt fields, that the strategy is WAG using the produced CO2, as was mentioned in the previous presentations, and of course we are introducing uncertainty modeling and optimization with the geomechanics constraints is one of the research lines that myself and my colleague Bernardo Horowitz are going to work in the near future. One important aspect of our research is that as we are injecting CO2 in carbonates, we expect to have water acidification and calcite or mineral dissolution that will change porosity and permeability, and also will trigger the water weakening phenomena, that is the influence of mineral dissolution precipitation on the geomechanical properties of the rock, strength and stiffness of the rock. So related to this topic, I will present in the last slides of my presentation a GIP that we are a joint industry project that we are proposing together with CSIRO and LNCC. So the motivation for the presentation on fault reactivation and CO2 injection, but also the motivation for our chair, is the Brazilian pre-salt that accounts for more than 60% of the total Brazilian production. And this paper describes a very interesting milestone, that is over 100 well equipped with intelligent completions. And in fact, these recent papers by Petrobras engineers that are working at the pre-salt area corroborate with our main research objectives. They postulated main challenge to be addressed that we use as this inspiration to our research program. So for instance, the modeling of reservoir properties take into account faults, vugs, karsts, and natural fractures. So it is related to hydromechanical and chemical phenomena. Reservoir and cap rocks integrity to avoid fault reactivation. This is related to geomechanics, and also chemical phenomena if we consider that we are injecting CO2 in a carbonate reservoir. Well, stimulation in order to promote the solution of some rock grains or create small wormholes into the formation, so it's directly related to geochemical phenomena. Perform water alternate gas cycles on injectors using CO2 and hydrocarbon gas. So it's again, it's multiphase modeling to account for reactive transport. And finally, manage gas injection in order to minimize GOR increases on producer wells that is linked to the robust optimization area of our chair. Well, Brazil is the third largest global player in potential carbon storage. It's important to mention that. And for this reason, we believe that our CO2 injection modeling work would help to ensure the safe deployment of CCS projects, not to mention to optimize the economic development and operations of EOR projects in Brazil. Regarding the methodology of this research line of fault reactivation in CO2 injection and carbonates, I would like to show the methodology and the main components of the methodology. You have three main components. The first one is the outcrop analysis. In this case, we have a very nice outcrops that is the Araripe Basin crater formation in the northeast part of Brazil, and our colleagues at the geology department, Tiago Miranda and Antonio Barbosa, are working on this, and also Virginio Henrique, they are working the characterization of this this very nice fractured, naturally fractured formation with fractures at different scales, and also the presence of faults. In this, they just presented a paper and on this describing the structural evolution of this fault. This is the Triunfo fault zone that marks the northern border of the Araripe Basin, which is a structurally complex region that represents the geological contact between the basement and the sedimentary basin. This is a Cretaceous fault zone that strongly influenced the structural control of naturally fractured reservoirs. They provide a structural map that characterize the architectural elements of the fault, that is the core zones and damage zones and fracturing the damage zones, that in fact we are incorporating these features in our numerical model. So we are embedding our finite element mesh with these elements of the faults, discretizing each one of these elements and then upscaling. So this is the idea. And because these layers of materials they have different properties that I'm going to show very quickly. Another important aspect of these outcrops, the outcrop analysis, that the outcrop provide us samples for our lab testing. So, for instance, we have here this fractured plug that we can direct shear in a shear apparatus that allows us to perform a chemical attack of the fracture, and you can measure the solid mass, change porosity using tomography, using fracture surface imaging. You can obtain the fracture change of ruggedness. So this was a very recent PhD thesis that myself and my colleague, Annalise Lima, supervised. And we can see here that using the shear apparatus, the change of the fracture strength, shear strength, when before and after the solution. So I mentioned that we have three elements, three components of this research. That the first one is outcrop analysis. Second one is the experimental analysis. We have a rock mechanics lab. And also the third element is the numerical analysis. In the numerical analysis, we consider the geomechanics and reactive transport. We had the opportunity during these years with Petrobras to apply our geomechanical software and our reactive transport to different problems related to pre-salt and post-salt. In the pre-salt, in the post-salt area, we apply our geomechanical code to evaluate fault reactivation analysis and sandstones. And also we are still working in this problem, introducing elements from outcrops, for instance, formation bands in the core of the faults, the formation bands, the influence of the formation bands, the influence of fractures in the damage zones. And this is a research that we conducted for many years with Leonardo Cabral at Petrobras, again with Leonardo Cabral and my colleague Igor, and a group of students. We work with the cap rock integrity due to the injection and related to dissolution of salt rocks. So we used our reactive transport to evaluate the possibility of dissolution of the cap rock in this pre-salt area. We are now working with data from pre-salt and data from outcrops to study the behavior of natural fracture reservoir, the coupling with geomechanics, how to couple. We are studying the coupled schemes to consider data from reservoir, data from outcrops, and also from experiments. And finally, I would like to mention a project that we have with Petrobras, that is the person there that are with us is Edgar Poyati, that we are studying the possibility, well, together with my colleagues, Leila Brunet and Licia Mouta, and a team of students, a postdoc, that is Jonathan. We are working in these caves in salt domes using solution mine techniques. So the idea is to inject seawater and produce brine and excavate a cave for storage, fluid storage purpose. So the idea is to store fluids, and what we are doing is for non-conventional conditions, for conditions that are not covered by commercial softwares because of the depth, the water rate, the temperature. We are working in the build of this cavern and the stability and the operational conditions of these caverns. Regarding the fault reactivations, we believe that it's a complex problem that but we believe that in oil reservoir with fault reactivation possibility, the definition of maximum bottom hole pressure of the injectors can only be conducted on a couple, based on a couple hydromechanical analysis, considering the complexity of the material. For this, at least elastoplastic model had to be used for the fault elements, for the fault domain. But that is not. There are other complexities associated to this problem. One of that was I mentioned already. That is, fault is a layered material that have a less pervious core and more pervious damage zones. So the permeability field change from the reservoir to the core, crossing the damage zone. Also, the geomechanical properties also can change the stiffness and strength of the material. And another source of complexity is the lack of information, because it's not easy to obtain all the detailed parameters of the fault. So we have to introduce uncertainty analysis that, in fact, we propose in the past. Recently, we proposed workflows on that. So this is the kind of analysis that we have. We introduce all this complexity in our simulation grid, in a hydromechanical problem, and we have the flow. We can obtain the flow patterns through the reservoir and faults and reactivated floats, and we can obtain the critical stress field, the displacement fields that will give us elements to analyze the cap rock integrity from the geomechanical point of view. But if you are injecting water and CO2 that will mix, that will at the end will give us a acid brine, we can have some geochemical phenomena. So geochemical phenomena will cause change of porosity and permeability due to the change of total mineral volume in the medium. So the variable that we are going to use to include the effect of porosity and permeability change in the total mineral volume that depends on the molar volume of the mineral, that is a property of the mineral, and the concentration of the mineral that comes from the reactive transport problem. So you can relate this change of total mineral volume with porosity and permeability using some laws that related directly permeability with porosity or with the minerals that are in the solid phase of the rock. And we can apply, for instance, for CCS application, as we published together with my colleague Eric Mackay and our student Ayrton and Jim and all the students for heterogeneous. And we can show how porosity and permeability fields will change when CO2 are injected. In addition, if you are in a stressed area, for instance, a fault crossed by a reservoir, this change can also, this change can also affect the geomechanical properties. This can be a critical situation that we have to include the effect of the dissolution of the rock in the geomechanics. The solution of precipitation, as well as we can have both due to kinetic reasons. In some part of the reservoir we can dissolve and other part can precipitate, as it is sometimes it's not instantaneous. And so we have to include in the stress strain behavior of the rock, the chemistry, and it can affect the properties, the geomechanical properties, or can directly cause volume change in the sample if it is loaded or under stress. To obtain this, we again use this total mineral volume as a state variable for the mechanical problem, and you can propose, you can postulate chemomechanical constitutive model where the volumetric strain due to chemistry can be computed using this variable, this state variable, and introduce this to a linear elastic law, including chemical volumetric strain, or elastoplastic law. It depends on how sophisticated we want our model to reproduce the phenomena that we have. With this model, we can simulate crystal growth and chemical compaction. I'd like to show very briefly an example of crystal growth. That is when you have the increase of volume of mineral due to a chemical reactions. In this case, is a civil engineering problem that we had. It's in Spain, expansion of argillaceous rocks with anhydrite veins that, due to the change of atmosphere conditions here, we have more hydration due to the increase of relative humidity of this environment. So we have here the transformation, the change of anhydrite to gypsum. So this mineral has a higher molar volume. So you have expansion of this formation due to chemistry. So it was published recently, and as a possible mechanism to explain this kind of phenomenon. We can use this similar kind of model to simulate also chemical compaction when we have a dissolution of the rock. In this case, it's artificial rocks that we build in our lab, the artificial carbonate rocks that we have a group of students. Katia, Cecilia was the first PhD that we had that worked on this. Katia, we have Lais and other students that studying this kind of problem, that we expose a rock under load, under constant load, and we observe what happened in terms of deformation and in terms of change of lateral stress using this apparatus. It's a odometric cell. And what you have here is the dissolution of partial dissolution of the rock due to the acid injection. So we can model this. We can see during this test a reduction of the volume of the sample and an increase of lateral stress. And you can use models such as the critical state model that allow us also to consider the decrease of the pre-consolidation stress and the decrease of cohesion as a function of a bounding variable that is related to mineral concentration. Finally, I would like to mention the JIP that we are proposing together in partnership with the CSIRO in Perth, Australia. The person is Melissa Kiut, and the other partner that we have is the Márcio Murad at LNCC. LNCC is the National Lab of Scientific Computing at Petrópolis in Rio de Janeiro, Brazil. And the title of this JIP is Impact of Rock Fluid Interactions on Stacked and Dynamic Properties of Fault Carbonate Reservoirs. We are in the phase of, we are still inviting companies to be part of this. And it is an experimental and numerical investigation on hydromechanical behavior of carbonates materials. So the objective of this JIP is to investigate the key issues in the assessment of reservoir subjected to CO2 for both EOR and CCS projects. So it's to investigate the fundamental constitutive behavior of the rock in contact with CO2 enriched brine, its incorporation to reservoir simulation using commercial codes, and this simulation should include the transport of CO2 plume and its interactions through the zones of a fault carbonate reservoir. So we are going to consider again this geological conceptual model of a fault with a core and damaged zones. The damaged zones has fractures, and so to achieve this objective, a strong experimental work at reservoir pressure, temperature, and stress conditions will be conducted. This is the main part of CSIRO. That is, we are going to do this in the lab at CSIRO, followed by numerical modeling at the plug scale. That's this constitutive behavior that is our UFPE main part of this JIP, with a gradual upscaling of the evaluated properties to outcrop and reservoir scales. That's Márcio Murad at LNCC is a specialist in this area, and this is the main part of LNCC in the JIP. So it's we have three institutions running this JIP, and with these ingredients. The ingredients are experimental microstructure, rocks physics, rock mechanics, and fault reactivation, numerical modeling of experiments, constitutive modeling and upscaling, and couple hydromechanical fault reactivation and reservoir modeling simulation. In the experimental work, the idea is to shear greystone blocks and to obtain different levels of shearing representative of the zones of the fault, core, damage zones, and reservoir. So the plugs will be extracted from these blocks and will be exposed in a triaxial apparatus to CO2 enriched solution, a brine solution, to have the different levels of chemical attack. So we have samples with the different levels of chemical attack and different levels of shearing. And the idea is to perform numerical hydromechanical and chemical simulation at plug scale in order to characterize different levels of chemical degradation as a function of fluid injection. And then numerical hydromechanical flow-based upscaling to equivalent properties of damaged zones and fault as a unique material. So there is, we have to perform upscaling work from plug scale to outcrop scale and then to a reservoir scale, considering the fault as a unique material, as the final product is to generate plugin for commercial reservoir simulators. Finally, some conclusions. We are developing numerical tools capable to evaluate the integrity of reservoir and cap rocks. And and considering a number of hydromechanical and chemical phenomena. Special attention should be paid to the rock fluid chemical interactions, and consideration of chemical effects requires concentration is chemical species, the consideration of chemical species, reactive transport equations, and models for chemical reactions. We are using the solid mineral concentrations as state variables for the chemomechanical constitutive models. And the final and more important objective, I think, for the near future is to couple hydromechanical and chemical simulations at outcropping reservoir scales of fault reactivation, consider chemical attack, and different numerical coupling schemes. And finally, I would like to give to especially thanks energy simulation for this more than 10 or to 11 years of support to our group, and Petrobras for about 15 years of support in our groups. I would like to give you a number, and up to date we have 87 students supported by the energy simulation chair at UFPE. This consortium, and it's a huge impact in our research, a huge impact in our graduate program, a huge impact to our university at the end. So thank you very much for the support along these years. Thank you, Andrew.
Thank you, Dr. Guimaraes. It's quite an intensive and comprehensive program that you are launching or working on. A question from Dr. Iraj Oshagi is fluid injection effects on triggering earthquake an issue in Brazil? And are we considering pore pressure diffusion on fault zones?
Well, I don't have any information related to dynamic events in the Brazilian reservoirs due to fluid injection. To my knowledge, I don't think so. And the second part is of the question is the
pore pressure diffusion on fault zones.
Yes, it's expected if what we want to prevent is that the fault will not be reactivated. So the idea is that the fault that can be the fault in the beginning of the production can be a sealing fault, but depends on the level of pore pressure that it is imposed in the reservoir. This fault can be reactivated, and it is possible to have a diffusion and to have a flow through the fault if it become a pervious one. So the idea is that to prevent this reactivation to happen.
Okay, I need to combine these two questions, last question together. Is that CO2 is injected, so if CO2 goes to the faults and there's chemical, mechanical reaction, is that considered?
Yes, the idea is to couple the effects of chemistry, and up to now it's a one-way coupling, so the chemistry affecting the geomechanics. But you can have, for instance, two-way coupling if you consider that crystal growth stresses will change for instance, the equilibrium constants of the reaction. It is a possible second-order effect that you are not considering, but yes, the idea is to consider the coupled phenomena more in a one way when the chemistry will affect geomechanical properties of the medium. Okay,
so just to wrap it up here, I am really pleased to see that from Computer Modeling Group, which is one of energy simulations industry members, Dr. Vijay Srivastava is offering a discussion with you to see if they could enhance the GEM program capabilities to accommodate some of the modeling ideas that you've got. So please, this is part of our technology transfer exercise as well. So please continue your discussion with CMG.
Yes,
so thanks again. Yeah,
it would be my pleasure to have this meeting and to discuss with.
Wonderful. Thank you very much.